Today, we are going to address some common challenges in MS data processing and analysis and show how ACDLabs software can support the deformulation workflow, specifically by addressing the following steps that are common in this workflow. So firstly, to automatically separate all chromatographic components. Secondly, to identify these components. And thirdly, methods to store and leverage this information and expertise that you as scientists may have. So once we've gone through these steps, we are going to switch over to the software, and Anne-Marie will give us a live demonstration of how our tools can be used. So first, a quick introduction to the ACD Spectrus platform. So ACD Spectrus is a vendor-neutral software platform that can support many different vendors, data formats, and software interfaces. So we support many of the large vendors, as well as many different open data formats, such as MZML, as well as emerging data standards, such as allotrope. So what are the challenges that you are, as scientists, you are facing? So as scientists, you may be being asked to detect and identify compounds more efficiently, despite the fact that there are many challenges that are common across the industry. So these may be shrinking analytical group sizes, so decreased number of analysts, as well as a pressure to perform more diverse activities and perform a wider range of analytical techniques. Finally, we're seeing there's an increased amount of outsourcing to CROs, where where you need to combine internal and external analyses, and this becomes a challenge. So these challenges result in quite a few different anxieties that are shown on the slide over here. Some of the common anxieties are listed. However, today we are going to be addressing the anxiety, are we identifying all possible unknowns? These are some of the worries that come up, and there are too many different aspects for one deformulation expert to address initially. So if we take a traditional approach and obtain the data, then we're taking a look at the separation. So a major question is, are peaks co-eluting? Then once we're taking a look at identification, questions that you may be asking are, if I've done a database search against a library, do my databases cover enough chemical space? What libraries are available to me to search? Have I identified these structures correctly? Are these isomers? And all of this can be quite time consuming given the high number of possible structures that you could be using. Finally, there are questions about saving this knowledge. So where can you store it so it can be used again for subsequent analyses? How can I accurately report it? How can I leverage previous knowledge to save time on routine analysis? And how can this knowledge be transferred to other members of the group? So these challenges can be grouped into three main areas: time, resources, and expertise. So let's take a look at how our software can support the deformulation process. So if we take a look at step one, which is separating components, our software can assist in extracting components and automatically creating a table of components where all components in the sample are listed. Step two, where you would identify these components, our software has tools that assist in searching libraries either by spectra or mass. So step three would be storing this data and leveraging your expertise. So our software has tools to assist in storing live data rather than a static PDF report, as well as identified structures in a database. So let's take a look at these steps in more detail. So step one, separation of components. So here you would identify your peak of interest in the chromatogram, and then use a tool in our software called IntelliExtract, which allows you to automatically extract all extracted ion chromatograms and separate out the components. So once we know what components we're working with, we can move on to identifying the unknowns. So let's take a look at how we're going to identify these components. So the first step, we'll be doing a spectral search for known unknowns. So once we have our chromatogram we have identified all the peaks that may be co-eluting, we would obtain high-res mass spectrum data and collect either MS1 or MS2 spectrum. Then what we can do is we can do a spectral search against either commercially available spectral libraries, such as the Wiley-NIST library, or using a user-created database. These matches will then be listed in the table of components for the scientist to review and to identify any components that can be identified spectrally. The next step will be to generate some molecular formula for the remaining unknowns. So here we can identify the molecular ion. Then we can select that from the table of components and start specifying some constraints for the formula. So these constraints could be things like the type of elements that are allowed, as well as the ranges of these elements. Then we can review and select the generated formula and select the most likely formulator for the unknown. Then we can take this mass and the formula, and what we can do is we can do a mass search against a commercial database. So because these commercial databases are very large, what we have tools that are optional that allow you to include and exclude specific fragments depending on some knowledge that you may or may not have about the structure. So here we would search libraries such as ChemSpider and the PubChem databases, and then choose the best structural candidate for from the range of possible structures. And this process can be repeated for all other peaks of interest. Finally, once we have identified all of our peaks, this information can be stored in a database. So we can store live analytical data along with all the structures and the table of components. And this information can then be leveraged for subsequent analyses. So if we take a quick look at overview of the workflow. So first, we're collecting our chromatogram and high-res MS data. Then we're going to take this chromatogram, extract out all the XICs, take a look at the corresponding MS1 and MS2 spectra. Then we can do a search, spectral search against either a user-created database or a commercially available library such as Wiley-NIST, and identify the candidate structures. For the remaining unknowns, we can start generating formula, then do a mass search against libraries such as PubChem and ChemSpider, and identify the remaining candidate structures. So to put it back to the steps that we looked at in the beginning of this presentation, step one, then once we have identified the candidate structures, we would store this data so it's available. So step one will be to extract out all of the components and automatically create the table of components using IntelliExtract. Step two would be to do spectral searches and mass searches. And then finally, step three would be to store this data. So our software supports your deformulation process by giving you the tools to do an automated deformulation of complex samples in 3 steps, and allows you to move through this workflow much quicker and to address some of those challenges that we brought up in the beginning of the demonstration, the slideshow. So now I'm going to hand it over to my colleague Anne-Marie Smith, who is going to move on to a demonstration of these tools in the software.
Thanks, Nikki. So hopefully everybody is seeing my screen now. So this would be our Spectrus Processor interface. And we're going to walk through those 3 steps that Nikki explained just within the software, so you can see how things are actually functioning. So the data set that I have open here right now is an LCMS data set. It was collected on a high resolution instrument. And for the purpose of this demonstration, I've set the analysis region that we're interested in from 4.5 to 5.5 minutes. So you can see that there's a region of the chromatogram that is shown in white. That is the analysis region. And if you're wondering, can you expand that and change that? When I'm hovering my mouse over the edge of that, you can see I have double arrows, and that will allow me to drag and expand. Okay. So the first step of the workflow that Nikki had explained was separating components. So there are two ways to do this within the software, dependent on whether you're going to actually search a user-created database, or if you're going to go with the second part of the workflow, where you're just looking at generating the formula and then searching ChemSpider and PubChem by mass. If you're going to do just the mass search, then to separate the different components, you'd be using what we call IX2, which is IntelliExtract. And this is merged into our tool for doing the library searching. So we'll talk about that as I go into our IXCR tool. So I'm just going to open that up quickly. And so these options that we see at the top here, this is what you would have seen if you had clicked the IX2 button, just kind of putting things in perspective for people that have used the software. So we have just a few options that you have to set up in order to actually do that extraction. So that's these first three options here, the signal to noise, the peak shape similarity, and component abundance threshold. That's what's required in order to do that separation. And if you're finding that components aren't being separated how you'd like, then you can alter these parameters to get better separation between them. So this is going to do the extraction of co-eluting components. That's the big piece here. The second portion that we see down below is what we're going to use for the spectral search portion. So as Nikki had mentioned, you can search by MS1 or MS2 spectra. So typically MS1 is more likely to be used with GCMS data, and MS2 would be with our LCMS data. If you're collecting multiple collision energies, there is an option to filter by collision energy. So this would be, you can set a range of different collision energies or discrete values. And similarly, you can also do filtering by retention time. So this is filtering the results that come back from the extraction to the database. The last portion here is relating to the library itself. So you can display several hits for each component if you're interested. You could also lower this down. So if there is only one hit, you'll just see one. If there happens to be 5 hits, we've limited it so that you only see 3 of them. So you have the flexibility there. And then finally, we have the HQI threshold, which is the hit quality index threshold. So this is going to be how similar your experimental spectrum is to that that's found in the database. So you can alter that as you see fit, depending on your sample and what your database contains. So I'm just going to open up the different databases here. And what we can see is that I've created this database here is a user-defined, user-created database, so something that I made myself. Whereas these other files that are listed below are commercially available databases. For instance, the one that I'm going to use today in conjunction with my user-created database is one of the Wiley NIST databases. So I'm going to go ahead and click OK on this. And the software is going to run through the processing. So it's going to do the extraction, so what we often refer to as the componentization. So determining those co-eluting components, and then it's going to do the library search for us. Once it's finished the library search, then we can see the results, which is what we're looking at right now. So we can see now that we have some structures in this table, and we also have a mirror plot here. So when we did the search by MS2 spectra. So we're seeing here a mirror of the experimental MS2 spectra to the library spectra. Okay. And if I select on a different component, then you'll see that everything has updated. So the mirror plot updated. I also can see the individual scan results, and my component, like I've selected, has moved to the correct retention time in the chromatogram. If you had just done the componentization without the library search, your results would look more like line 3. So line 3 is, what we're seeing is there was no hit in the library for this component. So I'm going to select on that for a second. And I have, my spectra has now been updated. So the other workflow that Nikki had mentioned was, well, if you don't have a user-created database, or if you have hits that are not found in that database, what can you do instead? And so that's the portion where we talked about generating formulas and searching other databases by mass. So I'm going to select my mass spectrum here. So you'll see there's a yellow box that appeared around the spectrum. And I have now a red arrow as I hover over the peak of interest. If I right-click, I can get access to some other commands within the software. So I'm going to select Formula Generator. And because I accessed it in this way, the software automatically pulls in the MZ value for us. So you don't have to manually type that. The next piece that we have to set up is the different atoms that we're interested in for generating the formula. So you'll probably hear me say this again later on, but the more you know about your compounds, the better the results will be, and the more narrow you can make those results that come back. So in this case, I've set different allowances, so a minimum and a maximum for the various elements. If your element isn't shown in the default list here, you can add it, so you're not restricted. So I just right-clicked, and then I have the option to add additional elements. And at this point, I'm just going to go ahead and run this formula generation. And we'll see pretty quickly the software has generated, 2 different formula for this mass. And we can see an error value that's associated with that, as well as what we refer to as the formula fit quality. So this is a measure of similarity between the calculated and experimental isotope patterns of the different compounds, so of that formula that we're looking at. So if we see maybe it's possible that you have more formula that have come here. Maybe you want to use a range of formula for the next step, but maybe you've decided that this formula is definitely the one that's of interest. I can right-click on that and annotate the peak. And what we'll see is that there's a little annotation that's been applied to the spectrum. So it just kind of makes it easy for us to see it as we move forward into the next step. I'm going to go ahead and close this window for a second. And we're going to look at doing the search into PubChem and ChemSpider. So again, I'm going to right-click and select Structure Search. And I bring that up. Again, we can see that the mass has been populated. I have my tolerance set here, so I set this a little bit wider, 20 ppm. And I'm using the formula information that I obtained from the formula generation that I had just run. So when I had looked at that, I'm just going to slide this over to the side here. We can see, we can compare to the formula that's here. And I've put in a little bit of a range just in case maybe the other formula that was generated is correct. I want to look at the various structures that could come back. And then the other piece that Nikki had mentioned was that there is the ability to put an include and exclude list. So certain fragments that might be of interest. So for instance, you could have maybe a phenyl group and you say that must be present in my structure, maybe your structure does not contain any alkenes or something like that, and you can apply those lists. So these are user created, which will help narrow down the results, and you can change these and save these so that you can use them multiple times. You do have the flexibility to run this search just with the mass, but again, the more that you know about your compound, the more information you can provide the software, the better the results are going to be. So in this case, I do have a check mark beside the elemental composition and the include list to try to narrow down the results that are going to be returned here. So I'm going to go ahead and click OK on this. And the software is going to search those two different databases. And pretty quickly, it's come back and said that it's actually found 9 different structures. So we're going to go ahead and click OK. The first prompt that you're going to see here is just telling us when the databases were actually updated. So here we can see the PubChem databases were actually updated this year, around a month ago. So they're pretty up to date. We'll go ahead and click OK. And we have what's called the table of search results. And here we can see the different structures that have been returned that match the criteria that we had just set. And what we could do is if one of these structures are of interest, we could then move that into our table of components. If you wanted to further interrogate these structures, we do have additional tools available to help you compare the fragments of these structures to the MS2 spectra, but we won't be talking about that part today. I'm just going to move back here, sorry. So I would copy my structure here, and I can paste that in. So here I can see this is the component that we were looking at previously that we didn't have a structure for, and now I've updated that structure. Once you're finished doing all of your processing, so you could repeat this step if you wanted for these additional components that are listed here. But if you're happy and you're content with how everything is, maybe you want to revisit it later on, you can go ahead and update this to the database. So here we see this little database icon with the plus sign. And there are a variety of different ways to update the information into the database. All of these do allow you to do searches with the different tools that we've talked about today. So typically what we would recommend is we'd have a conversation with you to help you determine which update mode is best suited for your application with how you want the data organized. And once you have it sitting in the database, you now have something that can be accessible by various people that you can do different types of searches on. So spectral search, a metadata search, or a structural search. And I believe we've had some other webinars or some quick start guides on our website that can help show you some of those additional tools within the database. So with that, Nikki, I think we'll switch back over to your screen and we can just do a quick summary here. So just to kind of go over what we talked about, we started with raw data, completely unprocessed. We looked at the separation of the components. So this was using the button that said IX 2.0 or IXCR. So it did the extraction, so the XICs were created. And then we moved on to the next step, which was the identification of the components. That identification was done in one of two ways. Through IXCR, we did a spectral search of either a user-created database or a commercially available database that is available in our format. So that was the Wiley-NIST database. The second option that we used was to generate a formula and do a search by mass with the flexibility to have an include or an exclude list. And then finally, we talked about how you can store this information into the database.